All right, this is gamma time. This might be the question that I've gotten the most questions all time for, so I love it. So for starters, right, we have this gamma function, which has a really, really weird definition, but gamma functions pop up in a lot of different places in math, right? So it shows up a lot in probability, especially, but like I say, queuing theory, climatology, finance, right? So a lot of different places have this sort of function in them, and it has some really, really cool features. So maybe I'll give you some cool features at the end, not of this video, at the end of all the videos here. So the gamma function is defined this way. Right, so we have this sort of definition of it. So one thing to be a little careful about is that t is here, but my integral is in terms of x, right? So t is a number, right? T could be 1, 2, 3, 4, 5 at this point, right? So you're taking x to some power e to the negative x. So for example, if I want to find gamma 1, right? So t is 1, so that's 1. I'm just simply going to get e to the negative x, which we know what this is going to be. It's going to be the limit as r approaches infinity of negative e to the negative x, evaluated from 0 to r. Right, so that's going to be negative 1 over e to the r minus 1 over e to the 0, so just minus 1. So when we take this limit as r approaches infinity, this thing goes off to 0, and we're left with, this the negative up front, my bad. So it's going to be a negative, I'm going to put that negative up front. So we're going to get this, so we're going to get negative 0 minus 1, which is just equal to 1, right? So gamma 1 equals 1. So let me do gamma 2 as well. We're going to use some integration by parts here. Right, so if I take our definition of gamma, right, so gamma 2 is going to equal this improper integral of x to the 2 minus 1, aka x, e to the negative x dx. Right, so this is going to be this antiderivative, same sort of idea with limits, right? Limit as r approaches infinity of 0 to r. So I do need to do a little bit of integration by parts here. This is also a good column integration question because x is going to behave nicely and e to the negative x is going to integrate nicely. So if I did column integration here, right, so here's my derivatives, here's my integrals, right, so I'm starting off with x, 1, 0. My integrals are e to the negative x, so negative e to the negative x, e to the negative x, right, that's always going to fluctuate. So when we take our derivative, we're going to get, or antiderivative, we're going to get negative x e to the negative x. Then we're going to get minus e to the negative x, right? That's going to be our antiderivative. So we're going to have this thing evaluated, negative x, e to the negative x minus e to the negative x, evaluated from 0 to r as r approaches infinity. So again, like this, we're going to get a lot of these e to the negative r's, right? So I'm going to be a little bit more, I guess, lax with those things in future videos, right? But we have this limit as r approaches infinity, negative x e to the r minus 1 over e to the r. Oops, that's some bad use of. Minus, well, I'm going to get negative 0 over e to the 0 minus 1 over e to the 0. Right, so all of these e to the r's, and this is going to be true for all of these ones in the future video, in the future kind of like working this gamma function, these things all just go off towards 0. So we get none of those things that matter. This term over here is also 0. So the only thing that lives on is this negative 1, right? So that's going to be positive 1. So we just showed that gamma of 2 is equal to 1. Gamma 1 equals 1, gamma 2 equals 1. And it might seem like this is going to be just a boring all ones functions, but tune in for the next video to see what happens. Bum, bum, bum. How's that for drama?